Hello everyone, my name is AidaTodriSanial, and I'm happy to give this talk at ISPD. I'll be talking about oscillatory neural networks from AI application and design challenges. I'll first start with the takeaway messages. So I'll talk about oscillatory neural networks, why this is an alternative energy-efficient computing paradigm, especially important for edge AI, and also how to compute with oscillators from important aspects such as materials, devices, architectures, to applications. And the need for this energy-efficient computing paradigm, especially at the edge, is due to its growing numbers, which are more and more applications are running at the edge and reaching in billions. And also this graph shows the embedded sensors on them and the amount of information which is continuously increasing, and also the limited capability for us as humans to be able to process this type of information. And the challenge comes mainly due to the von Neumann paradigm, so the classical computing paradigm that is mainly deployed on this type of edge devices. And this is due to the separation of memory processing, which also a lot of the energy is consumed on the data transfer. An alternative computing paradigm is the von Neumann. Beyond von Neumann is to look into, rather than the separation of memory and processing, is to have an intertwined where the memory and computation are all in one, so more brain-inspired computation. This allows not only for energy-efficient computing, but also to bring new functionalities and capabilities which currently are not available at the edge. And biological neural networks give an inspiration to be able to encode information. One of them is spiking, but also an alternative is in oscillations. So biological neural networks have this rhythmic behavior, they spike and fire. And also from neuroscience, we know that a lot of information, or the memories, are also based on the frequency of this neuron switching. And they are ubiquitous in neurocortex, in hippocampus, and olfactory. So think about this type of synchronization signal. So you might have seen from EEG signals. Now the challenge is to be able to compute with this type of signals or waveforms. So rather than from classical where 1 and 0 is your voltage, your VDD for a signal 1 or ground for signal 0, now the challenge is to encode this information on the phase difference between signals. Think about the signals shown here in blue and red, where they're in phase, there is a 0 degree difference between them. This is the logic 0. And if it's a 180 phase degree difference between them, this will be a logic 1. So this brings an opportunity to encode information rather than in voltage, but in the phase difference between signals. So you can imagine that this voltage now can be, the amplitude can be drastically reduced to also allow this energy efficient computation. To give a little bit of an insight into this, think about metronomes. You can think about them starting at a random time, and after a while they'll all be synchronized. Well, the same conceptual can also be thought about oscillators, where, for example, in this image here, each pixel is an oscillator, and the memory of this network, it's also on the coupling between these oscillators, where they perform an associative memory type of function, and after several cycles, they can actually provide what was memorized on that network. And they're very much inspired from Hopfield neural network, which perform intrinsically this associative memory type of application. And over the years, I've been leading a Neuron project, which is a European consortia. And the goal is to be able to implement computing in phase, so where information is encoded in phase between the oscillators, to implement an oscillatory neural network, but with novel devices. So with neurons as oscillators and the coupling between them based on 2D materials, so molybdenum disulfide or transition metal decalcinides. And for neurons are phase change materials where we are exploiting their hysteresis, such as shown here from VO2 devices, to be able to build this oscillatory behavior. So again, the conceptual difference between spiking neural network and oscillatory neural network, here for example for spiking you have a lot of information encoded on the spike rate, where you need to integrate to be able to understand if it's a 0 or 1. And in oscillatory neural networks you are continuously changing or looking into the phase difference between signals, so you have a reference clock or a reference oscillator, where this difference between them, the phase difference between them, can encode the information. So now let's look a little bit into the materials and devices of how to implement this type of oscillatory neural networks. From the material side, as I mentioned, for the oscillator, we need a phase-based or a phase transition-based device. And the one we've been using is vanadium dioxide, and it undergoes a phase change from insulating to metallic, triggered from the Joule heating. So the device has this type of hysteresis behavior. So this is the heating, and this is the cooling cycle. So this hysteresis between insulating to metallic also allows us to implement this as an oscillator. And here's a little bit more detail into how this device looks like. So this is a planar device. So you have vanadium dioxide, and you also have the two electrodes. You can think about shrinking this so you have several grains of this type of granular film from VO2. Another configuration is a crossbar configuration, where we have the VO2 is sandwiched between a top and a bottom electrode. And this allows much more denser grains and a much more also repeatable and regular type of device, which has less variations, but also has a much more sharper type of transition. And these are also some results in terms of, this is in collaboration with some of the partners in the framework of Neuron, where we have looked into, for example, granular film response in terms of the transition, so this resistance over temperature, hysteresis, and also here when you have a single grain or nanoparticle, where it allows this very sharp transition and a narrower temperature width. We have performed a lot of quantum mechanical type of simulations to understand the behavior of such devices and also the impact of electrodes. So one of them was to perform density function theory type of simulations to understand the interface between the VO2 and gold or platinum and gold, and also how this type of electrodes also impact the thermal resistance on this type of a device. We also investigated the MOS2, which behaves as a memoristic device for our coupling between the oscillators, where we were trying to understand what is the switching mechanism in order to be able to have a hypothesis for this type of MOS2 devices that provides the switching in terms from a semiconducting to metallic, or high resistive state, low resistive state. So we could think from the device operation that the concentration of the vacancies, so the sulfur vacancies, could cause this type of switching. So we saw, for example, perform simulation here with sulfur vacancies from 10 to up to 25%, but we still see that from the density of state, this is still a semiconducting type of device. However, if we apply that some of the electrodes, so for example the gold atoms, actually fill some of these vacancies, we see that indeed there is quite a drastic switching from semiconducting to metallic. So we believe that maybe this hypothesis of a migration of atoms to fill the sulfur vacancies could be the switching mechanism on this type of devices. We also looked into the various layers, so how many the layer thicknesses, so for example monolayer or 4-layer. We could see that the gold and also the interaction between the molybdenium disulfide and gold, and also between molybdenium and molybdenium disulfide. We could see that the interlayer distance between molybdenium disulfide and gold actually has a very limited metallization. While with molybdenium we can see that there is very strong metallization. However, it also serves as a layer to limit the interaction on the other layers. Thus, we believe that this type of behavior also gives insights that maybe a single layer molybdenium disulfide is not enough to be able to have a memoristic behavior. That's why we believe that it has to be 2 or more layers in order to be able to have this type of switching mechanism. So now that gives a little bit of a detail in terms of the material, but how do we make an oscillator device based on this? So from here, we performed a lot of TCAD simulation where we went from, again, from the material properties and to the device geometries, and then later on to circuits. So to begin with, from the TCAD, so the computers, the technology computer aid design, what we applied is to simulate the VO2 device, we simulated via the self-consistent, so the semi-classical transport via the drift diffusion mechanism, and by using all this continuity equation and current equation. And in order to be able to perform a very careful simulation, we were first to emulate the switching mechanism on the VO2 devices. So for this, we needed to emulate the physical mechanism of switching. So what we did, we modeled it as a mesh network, where you can see that these resistances go from insulating to metallic in order to be able to emulate this heating and cooling, so this resistance change with temperature. And also this temperature impact on the device also has this percolation progress. So it means there are certain states where both metallic and insulating grains are also found. And so this is so it's a gradual transition from one state to another, and this is not necessarily homogeneous. What we did, we performed a lot of simulation from TCAD that we also calibrated from experimental data in order to be able to capture this resistance versus temperature type of behavior. And we also have derived the IV, so we have performed also IV simulations, which are also benchmarked against experimental data, so we can now be able to utilize this for circuits and architectural level exploration. So this is what it means to have an oscillator. So we have the VO2 device, which is coupled with an external resistance and capacitance, which now we can provide the oscillatory behavior, which links these material properties with the oscillator figure of Mears in terms of frequency and also the amplitude of switching. So from the devices, we go to circuit level simulation. So in order to be able to implement this for circuits, we need to know also how to bias. So there are various ways, as I mentioned earlier. It can be with a resistance and external capacitance, but it can also be with an external NMOS type of device where the gate is used to be able to have this to scan the various possible curves to have the oscillator, the device, oscillate in the NDR region of the VO2 device. So this provides us more flexibility in order to be able to bias or to have the device operating in the NDR. And we also have the derived all the dynamics in terms of the circuit equations to be able to derive the how this type of oscillator would perform. We also have looked into the coupling, which is very important. So how would you couple such these devices, or resistive or capacitive? And we can see here in terms of initial phase of the oscillators for two coupled oscillators, and as a function of resistance, you can see that with low resistive, so for example 10K, they're in phase, so the waveforms are completely overlapped. So it would be like a logic 0, so white in terms of image encoding, and out of phase would be when this resistance is quite large, so that means there is no current flowing between them. So you can see this waveform, so they're 180 phase degrees, and in terms of the output, there will be like a white and a black pixel. So we have explored and also implemented quite a lot in terms of resistance coupling, but also we have looked into the roles of capacitance, and we have seen that adding capacitance provides more flexibility in terms of how to get the oscillator synchronization, and we also have more accuracy with them. We have also implemented quite a lot of demonstrators from PCB in order to be able to have as a proof of concept. So just to kind of give you again a little bit more intuitive how this works, so you can think about a fuzzy input image, and you can look into the various oscillator dynamics, which they do synchronize, and they lock a few cycles in order to be able to retrieve what was memorized in them. You can see by now we only have encoded information in black and white, so 0, 180 degrees, but they can also be more possibilities to encode more information. So here is another demonstration of implementing oscillatory neural networks in ASIC. So what we did is we taped out in 65 nanometer node a 16 oscillator, coupled oscillator type of network. So you can see here, this is the synaptic, and here are 8 neurons and 8 neurons to be able to have a symmetry type of design, where we can use this type of architecture to be able to solve graph problems. And the idea is to, on these coupled oscillators, we can embed graph problem, for example, as max cut, where each node is an oscillator, and the coupling between them represents the weights of the graph. So here shows, for example, for this type of a graph, the solution, so you can see the phase evolution. So this is a phase plot where over the cycles, so you can see how they initially start here, and with time, so with up to 100 type of runs, we can see how the phases of each of these nodes or each of these oscillators evolve in time. So you can see that they are very much some of them are around 0, and the other ones are around 180 phase degrees. So you can see they're completely binarized in order to be able to provide the solution, or which sets of nodes or oscillators are in one side or the other sets of oscillators on the other side. So it's like you are cutting the graph into two to be able to have the maximum edges between them. And what is interesting for oscillatory neural network for this kind of problems is that it requires a very small amount of computation cycles to be able to derive to a solution. So this is a very interesting with respect to solving NP-hard problems, but also to be able to solve them potentially in a reasonable amount of time. So polynomial or maybe logarithmic. So this is also the hope, to be able to see how this type of oscillatory neural networks can be able to accelerate solving NP-hard problems. We have also benchmarked with various state-of-the-art type of hardware. So in terms of neuromorphic, but also accelerators. So here are the accelerators, and these are more neuromorphic, such as Loili, True North. And this is the VO2 type of ONN computation. So we also have, with respect to the scaling of the VO2 devices, showing that we have relatively competitive with respect to the energy, even though we don't operate in very high frequencies, but just to show that we have a competitive solution that could serve as a potential accelerator for certain tasks. And other benchmarks and applications that we have also tried is on implementing this digitally on FPGA to be able to see what kind of AI applications we can target. And in digitally, the oscillators are digital, so type of linear shift oscillators, and the coupling, it's on registers between them. So the type of applications we have tried is on digit recognition. So you have images, fuzzy images from streaming from a camera that you are recognizing on the ONN. We also have tried it for robotics, so very small robots with sensors, and be able to do obstacle avoidance. And we also have tried edge detection for feature detection on real images. So for example, this one gives a little video of, for example, here on this, it's the phone providing fuzzy images, and here is the corrected image on the screen. Here's also the obstacle avoidance ONN, where we are using two small ONNs, so 5x8 and 1x8, to be able to first convert the input image from the sensors into an image that ONNs can process, and then from there be able to determine a command for the motors. And this is, for example, another type of where we see the robot avoiding obstacles as it finds its way. So with that, I would like to probably wrap up, but the future work is to be able to process dynamical data with this type of networks, and not only solving inference type of problem, but be able to perform more classification and also to solve other type of more, for example, sound or other type of sensors, touch sensors, so other type of sensor that we can process. And this is also another ongoing work on implementation for analog ONN is an AI accelerator, but using VO2 type of devices, but also ReRAM type of crossbar array for the coupling between them. I would like to say a quick thank you to my team. I have two teams at the moment in Montpellier, France, and also here at Eindhoven University of Technology, where I started a new lab. So I'd like to thank you them for this work is thanks to also all their efforts. And with that, I'd like to thank you for your attention.